Welcome on board. This is Design the Engineering Process, a channel where we give a walkthrough on process engineering operations and design. Before we start today's content, if you haven't watched our previous content, I suggest you start with that to avoid getting lost during today's content. You can find the link below in the description. Let's dive in. In today's content, we will be looking at about 4 equipment used in process engineering design and simulation on ASPEN HYSYS. You can see them down here when you click on your model palette. They pop up all the instruments used for modeling and simulating on ASPEN HYSYS. For today, we'd be looking at the first 4. The mixer, the tea, the heater, and the cooler. Let's start with the mixer. What exactly is a mixer? A mixer is a device used to combine 2 or more fluid streams into one, ensuring thorough mixing of fluids. A mixer in a pipeline ensures that multiple fluid streams blend homogeneously. Looking at the visual aid on the left-hand side of our screen, you can see that we have 2 inlet streams and a single outlet stream. Now, the concept of a mixer is to mix 2 or more streams into a single stream. With that, it is deducted that a mixer can have any number of inlet streams, but only a single outlet. So, something very important we need to know is that the mixers are governed by the continuity equation, which states that the mass of a fluid remains constant as it flows through a system. In other words, the amount of fluid entering a system must equal the amount of fluid leaving it, assuming there are no losses or accumulations within the system. This principle is based on the conservation of mass. So, translating the continuity equation, theoretically, we can write it as the flow rate of stream 1 plus the flow rate of stream 2 equals the flow rate of stream 3. Mathematically speaking, Q1, the Q signifies the flow rate. So Q1 plus Q2 equals to Q3. The summation of Q1 and Q2 gives us Q3. That's basically the mixer, the stream 1 of the mixer, adding up with the stream 2 of the mixer to give us the outlet, which is the Q3. In another narration, still saying the same thing in other words, Q in, which is the Q inlet 1, plus the Q inlet 2 equals the Q outlet. So, for the purpose of general knowledge, we majorly have 2 types of mixers, the static mixer and the dynamic mixer. The static mixer consists of stationary mixing elements placed within a pipe. These elements create turbulence as the fluid passes through, mixing the streams without any moving parts. They are often used for continuous processes and are energy efficient. And for the dynamic mixer, it uses mechanical agitators or rotating parts to mix the fluids, typically used when fluids have different viscosities or when intensive mixing is required. So, before we get to talk about the second equipment in our model palette, which is the tea, we're going to be taking a little bit of a detour, which is very, very important. On the right-hand side of the screen, as you can see, we have what we call a splitter. What exactly is a splitter? A splitter is a device or a fitting used to divide the flow of fluid from one pipeline into 2 or more streams. It functions similarly to a T, but the key difference lies in its nature and purpose, which is primarily to distribute fluid evenly across multiple paths or branches. Now, as for a T is also known as a pipe T or a T-joint. It is a fitting that allows the connection of 3 different pipes. It is shaped like the letter T with 2 main ends aligned in a straight line and a 3rd branch perpendicular to the other 2. T's are used to either combine or split fluid flow in a piping system. Please take note. A T is different from a splitter. Now, you might be wondering, why are we talking about splitters? A splitter, as you can see, the difference between a T and a splitter, let's highlight it. The T has a letter T-like shape. As for the splitter, it does not have a specific shape. That's one of the difference. The second difference is that a T can operate either as a mixer or as a splitter. A splitter can only operate as a splitter, splitting streams. Now, the third difference, which is the most important, is that the T, when operating as a mixer, can have a maximum of 2 inlets and a single outlet. When operating as a splitter, the same T, when operating as a splitter, having a single inlet can only have a maximum of 2 outlets. But for the splitter, the case is different. It's different. Having a single inlet, the splitter can have numerous amounts of outlets. There is no specific number or restriction for the splitter. So that's the most important difference between the T and the splitter. The reason why we're discussing this is that when we get to model, you'd see that the second equipment labeled as the T is actually less of a T and more of a splitter in ASPEN HYSYS, because the T, the so-called T does not really behave like a mixer. It solely behaves like a splitter, and it's not restricted to having only 2 outlets for splitting streams. It can have numerous amounts of outlets, so it makes it more of a splitter than a T. Please do take notes. This is very, very important. Similarly to the mixer, the splitter is also governed by the continuity equation. Even though the splitter is the opposite of the mixer, with that we can re-engineer the continuity equation backwards and mathematically have Q2 plus Q3 equal to Q1. Take a look at our visual aid on the left hand side. If you can remember, from the mixer, we're having 2 inlets and a single outlet, but this time around, having the splitter, we're having a single inlet which splits that single inlet stream into 2 outlet streams, stream 2 and 3 coming out. So looking at that mathematical equation, we're having Q2 plus Q3, which are the 2 outlet streams amounting to the same initial Q1, stream 1, which entered the system. The system is the splitter in our case. Furthermore, saying it to be the flow rate of stream 2 plus the flow rate of stream 3 equals the flow rate of stream 1, the initial stream entering the splitter. So just like the mixer, for extra knowledge, we majorly have 2 types of splitter: the two-way splitter and the multi-way splitter. The two-way splitter, the most common type, where the fluid is split into 2 equal or unequal branches. As for the multi-way splitter, you use to split fluid flow into more than 2 branches, often seen in complex piping systems. So, important notes. We've discussed every single thing here. This is more of a recap. Splitters can have any number of outlets but a single inlet. We've discussed that. Mixers can have any number of inlets but only a single outlet. We've discussed that. The difference between T's and splits is that a T is mostly used as a fitting on a pipe system for either splitting or combining streams and can only have a maximum of 2 outlets or inlets depending on the operation, mixing or splitting. As for the splitter, it is only for splitting streams and can have any number of outlets with only a single inlet stream. So, this is just a short recap. Make sure you don't forget what we just discussed right now, because it's very important. It's where the whole difference between the T and the splitter lies. We're back to the modeling environment currently. We're ready to start modeling with the 2 equipments we went through, the mixer and the splitter, which is labeled as the T in our model palette. So let's start with the mixer. I'm about to create a stream. I'll be naming this propane. Now, remember that for us to create a stream, we do need to select our component list and fluid package. For those of you who do not know how to do that, that was our previous content, and I would still be dropping the link in the description so you can watch that and get on track with us. So let's head to our composition. Today we're going to be working with mass fractions. Please do take note. Propane. This is a stream named propane, so it's going to be 100% propane. And to signify that, we click the value to be 1 mass fractions. Remember, we have to impute that again. 1 mass fraction. And okay. Okay. Oh, that's a bit of an error. Let's try that one more time. Mass fraction 1. Okay, and we have successfully added the composition 100% propane. Back to the conditions. So let's say, let's give our stream a temperature of 25 bar, a pressure of 30 bar, a flow rate. Remember, we're working in mass fractions, so today our mass flow rate is going to be, we're going to be imputing the mass flow rate manually, and that's going to be about, let's say 10. Now, as you can see, the fourth variable, which is the phase fraction / vapor fraction, has been given to us automatically by ASPEN HYSYS, propane. So we have successfully created a stream. Now, the first equipment we're going to be using is the mixer. As you can see, it has a red color. What this red color means is that the equipment is empty, no stream has been attached to it, and in some cases you might wrongly attach a stream to an equipment. It doesn't really have to be for lead mixer. Every single equipment in ASPEN HYSYS, whenever it's empty or it's wrongly connected to a stream, it remains in this red color. So remember, the conditions for a mixer to actually operate is that it combines 2 or more streams. So we would need to create another stream of propane, another stream for it to actually do its work. Remember, the mixer has 2 or more inlets but a single outlet. So let's create another stream of propane. Actually, let's create 3 streams of propane. 1, 2. But I want us to actually try and obey the continuity equation, which talks about the flow rates of different streams. So we're going to be giving them different flow rates. For the first propane stream, as you can see, our flow rate is 10 kilogram per hour. So let's do this very lazy and convenient thing of defining the stream. Using propane 1, we define the stream. With that, we have copied every single value from the propane stream down to the second stream, and let's name this stream propane 2. And let's just change. So it's given us molar flow, and that's not what we're working with. We need to manually impute our mass flow. We're having our first propane stream to be 10 kilogram per hour. So let's make this one about, let's make it 20 kilogram per hour. And with that, we have successfully created the second stream. And let's do the same process for the third stream. Define the stream using propane. And we take off the molar flow. Remember, we're working with the mass flow. This time around, we're having the first stream to be 10 kilogram per hour, the second stream for propane to be 20 kilogram per hour. Let's make this 80 kilogram per hour. Yeah, with that, we have successfully created this third stream. So remember, the continuity equation states that what goes into a system must amount to what goes out of the system, provided there are no losses or accumulations within the system. So with that, we expect that the total flow rate we have for the 3 streams is equal to 100, because we have, for this stream, we have 10 kilogram per hour. For the second propane, we have 20 kilogram per hour, and for the third one, we have 80 kilogram per hour. So going by the continuity equation, we're expecting a single stream which carries 100 kilogram per hour. So to operate the mixer, we double click on the mixer, and this is how the interface looks. We're on design connections. This is the inlet where you select your inlet, and this is the outlet. Now, for every equipment in ASPEN HYSYS, the outlets, we'd always need to label the outlet. For the inlets, we already have them on ground, so we connect inlets. But for the outlets, we label them because remember, it's a process. And when you put your feed into a process, you're expecting products. We do not know the products. The products are a result of the process. So this is what we're doing. We just label it and allow ASPEN HYSYS to give us the product. So let's label this as mixed propane. And our inlet streams, we connect our inlet streams. This is propane 1, we connect that. You just click on this arrow and it gives you propane 2. We forgot to name this third stream of propane 3, but it's not much of a problem. Propane 3. With that, we have our 3 streams successfully connected. You can see this. Let me just move this away. You can see we have successfully connected the 3 streams and the outlet is ready. So we have successfully operated our first equipment, which is the mixer. So just to make things symmetrical, yeah, much better. So you can see that we have a change for the color of our equipment. Earlier when it was empty, we were having a red color. So what this silver color means for every equipment is that you have successfully connected and operated an equipment in ASPEN HYSYS. When the color changes, that's what it means. It's just like our streams. Having a sky blue stream means that we have an empty stream, but the moment we successfully create the stream, it turns to a dark blue stream. So it's the same thing for the equipment. Colors matters. The color information matters in ASPEN HYSYS, so we need to pay much attention to that. So with this, we have successfully created our outlet stream for the propane. That's the outlet of the mixer. As you can see, we have 3 inlets but a single outlet. That's a mixer doing its operation. So for the continuity equation to be successfully obeyed and for the mixer to be 100% correct in operation, we expect us to be having an outlet reading 100 kilogram per hour flow rate, mass flow rate. With that, you can see we have 110. Where did we get an error? Oh, the total going in was 110, actually 100 kilogram per hour. It was actually 110. So just to make the confirmation, this is the first stream, 10 kilogram per hour. The second stream, 20 kilogram per hour. The third stream, 80. 10 plus 20, that's 30. 30 plus 80, that's 110. So we're correct. Let's just fix this up. Propane 3, much better. So with that, we have successfully operated our first equipment, which is the mixer. Now to the second equipment, which is our T, which is actually a splitter but named T in ASPEN HYSYS. So remember what we said, that a T, the major difference between a T and a splitter, which we will actually get to see while modeling, is that the T can have only a maximum of 2 outlets. But this time we're going to have 3 or 4 outlets. Let's make it 3 for us to actually see that this is not actually a T but more of a splitter in ASPEN HYSYS. And this same T cannot actually operate as a mixer also, like it implies for the operation of for the operation of a T. In ASPEN HYSYS, this label T can only behave like a splitter, thereby splitting streams only and having it can actually have more than 2 outlet streams. And that's what we're about to do. You can see that the initial streams are going into the mixer were 3. So what we're going to do, we're going to split this mixed propane stream back to the initial 3 inlet streams, but they're going to be outlets right now. I'm sorry if I sound a bit too confusing. It's going to make sense in a couple of minutes. So remember what we did for the mixer. You double click and you connect your inlets just like the mixer. It has the inlet section and the outlet section. So remember, you click on the arrow to select your inlets because you have it on ground. And as for the outlets, you have to label a name for them because we don't have them on ground. So we select names for our outlets. Now, one thing about ASPEN HYSYS, it's just like every single computer. When you name a stream, you cannot rename, when you name a stream a certain name, you cannot name a new stream that same name. Meaning you cannot have two streams having the same name. It's just like a computer. You cannot have two files having the same name. Causes an error for reference. So since we already have our 3 initial streams to be propane 1, 2, and 3, this time around we're going to have to be using another name. So for reference, let's be using their flow rates to actually refer to them. Propane. First stream of propane was having a mass flow rate of 10 kilogram per hour. So let's say it's propane 10 here. Then we create a second outlet stream to be propane 20, because the flow rate was 20 for the second stream. And the third one should be propane 80. Okay. So I'm sure you've noticed something different by now. When we operated the mixer, the moment we inputted all our outlets and inlets, it's automatically solved and did the mixing for us. But for the splitter, it's different. The splitter requires you to specify the ratio of split. For the mixer, you do not really need to specify the ratio of mixing, because a mixer is supposed to actually combine everything homogeneously, and that's what it did. But for the splitter, you need to specify the ratio so that ASPEN HYSYS knows how it's going to rationalize every single thing to every single branch or path you're having. And remember, we're sticking with their flow rates, so we're going to rationalize them back to their initial flow rates. And for you to do that, you click on worksheet and it brings you to this environment where you can see the attributes of every single stream you have connected to your T. This is for the propane 10 outlet that we just created, for the propane 20 outlet that we just created, and for the propane 80 outlet that we just created. This is the mixed propane inlet that is going into the splitter. So now we're going to specify, remember we're specifying the outlet flow rates according to their initial flow rates from the mixer. For this, remember we have their names referenced with their flow rate. So we're going to be having the split. It's the split for the propane 10 to be 10. What we need, the flow rate we need inside the first stream, which is the propane 10. The outlet stream, we need 10 kilogram per hour. For the second one, which is propane 20, we need 20 kilogram per hour. And for the third one, ASPEN HYSYS as always does this beautiful iteration process of giving us the third value the moment we have 2 given. And with that, we have successfully operated our splitter. So back to the modeling environment. Let's just space this up so it looks better. Get this down. And with that, we've successfully splitted them back to how they were looking initially. But for us to actually confirm that, let's go through their attributes. As you can see, propane 10 has the same flow rate of 10 from its initial propane that was entering the mixer. This is it. You can see propane and propane 10 having the same flow rate. Successfully done. It should be the same thing for the other 2 streams. 20 for propane 20 and 80 for propane 80. With that, we have successfully operated our second equipment, which is the splitter. So what we basically did, if you're a bit confused, is we mixed 3 inlet streams inside our mixer to a single outlet stream, which is the mixed propane, and we used our second equipment, which was a splitter, to split that same mixed propane into 3 different branches, like the splitter is supposed to do. So if this was a T, we wouldn't be able to have 3 branches, only a maximum of 2 branches. But since it's a splitter, we have 3 and we can have 4 and as much as we desire. With that, we have successfully operated our second equipment. But before we leave, I want us to try something very important. But before we try it, let's think. Remember that the vapor fraction third equipment we have in our model palette is a heater, and I'm sure most of us are conversant with what a heater is, both for us to make things proper. Let's go through it quickly. A heater is a device used to raise the temperature of a substance, typically through the application of heat energy. Some types of heaters include electric heater, gas heater, steam heater. For the fourth equipment, a cooler, which is the opposite of a heater, a device or a system used to remove heat from a substance, material, or space, thereby lowering its temperature. Some types of coolers include air cooler, water cooler, refrigeration systems, heat exchangers. So, for us to go through the operations of heaters and coolers, remember from the thermodynamic studies, we derive a relationship between pressure and temperature. In gas, mostly ideal gases, the relationship makes pressure a function of temperature. Further expressing the relationship with Gay-Lussac's ideal gas law, pressure is directly proportional to temperature with volume kept constant. Therefore, increase in temperature gives about increase in pressure, and the vice versa, which is decrease in temperature gives decrease in pressure. Now, for the liquids, it's a bit tricky. It's not like the gas, the ideal gas. It does not have a certain law relating the pressure to the temperature, but we do have some phenomena which do relate both of them, the pressure and the temperature. Phenomena such as vapor pressure change, change in kinetic energy of molecules, and closed system pressure buildup. So, before we head back to the modeling environment to check out our third and fourth equipment, there is something very, very important I need us to understand. Unfortunately, we were not able to discuss it in our previous content. The vapor/phase fraction. This refers to the fraction of each phase, typically vapor and liquid, present in a given stream. It ranges from 0 to 1. So it basically has the same nature as the composition, having the minimum value to be 0 and the maximum value to be 1. But there is a but to it. We cannot view the phase fraction from a perspective of percentage totally. The reason for this is that the 0 signifies pure liquid. That means our phase is completely liquid. And for the 1, it signifies that our phase is completely in gas state. So if I'm having 0.5 as my vapor fraction, even though we said we could not view from the perspective of percentage, let's say it's a 50-50 thing, which we call in thermodynamics, our thermodynamics charts, we call it the equilibrium, phase equilibrium, where we're having equal proportion of 2 or more phases. But in our case in ASPEN HYSYS, we typically deal with gases. ASPEN HYSYS, we deal with liquids and gas, or vapor rather. So if I'm having 0.5, I'm at equilibrium between gas and liquid. I'm having equal proportion of gas, equal proportion of liquid. So the tricky part is, if I'm having something like 0.1, what is that exactly? What phase, how do I represent what phase I'm currently in? So remember that our 0 signifies our liquid and the 1 signifies gas, pure gas and pure liquid. If I'm having something like 0.1, I'm still in liquid phase, but I'm generating more gases because I moved from my 0, I'm heading towards the 1, which is gas. I'm having 0.1, I had an increment. 0.1 is more than 0, so thereby I'm having more gas in my mixture. Let's just view it a little bit from a perspective of percentage. I'm having 90% liquid still and 10% gas. If I'm having 0.2, I'm heading towards the gas more, so I'm having 20% gas and 80% liquids. I keep moving up until I reach my 1, a state where I'm having plain gas. Now, the doing it backwards, coming from gas down to liquids, if I'm at 0.9, I'm having 90% gas and 10% liquids. I'm forming I'm forming more liquids. The gas and it's the state of gas. At the state of gas having 0.8, I'm forming more liquids. By that, you would say maybe I'm having a bit of condensation. Yeah, forming more liquids. But basically, I hope you do get the concept. From the 1 down to the 0, we're heading towards the liquid. We're forming more liquids the more we move away from 1. And the more we move towards 1, we're forming more gases. This is very essential to understand before modeling and simulating, because everything we do in ASPEN HYSYS is tied around the vapor fraction. It tells us a lot about a particular stream and a process as a whole. Time to get familiar with the third equipment, which is our heater. This is it, the third equipment, heater, having a red arrow going down. We drop it to the modeling environment. Now remember, what the heater does is that it raises the temperature of a body or substance from one point to another point higher, basically raising the temperature. So for that, we do need a stream which goes into the inlet of the heater and comes out hotter at the outlet. So as usual, we will create a stream. Let's name it propane, because propane is what we have as our component. Propane. So remember what we discussed about our vapor fraction, the 0 and 1 and the range. Let's make this a liquid, thereby being 0. And give it a temperature of, let's give it a flow rate first. The flow rate is very, very important in every stream. It's paramount, so you need to always include your flow rate. So let's make it 100 kilogram per hour. And let's give it a temperature of about 50 Celsius. Unknown composition, okay? Make it 1. Mass fraction. 1. Okay. Yes, with that we have successfully created a stream. So our propane is in the liquid state, which is 0, purely liquid. It's 50 Celsius, 100 kilogram per hour mass flow rate, and our pressure being 17.20 bar. So remember what we discussed about the pressure and temperature relation? When you do heat your temperature, we said that when you do increase your temperature, the pressure increases a little bit. So after heating, you're going to notice a change in our pressure. This is due to the relations that we did discuss, the relationship between pressure and temperature. So let's send our liquid propane stream into our heater. Propane. So as you can see, the design, connections, this is the interface for the heater. And I've already selected my propane. So we have something extra for the equipment, this heater equipment, which is the energy. Unlike our mixer and our splitter, where we do not need to include the energy, there is no energy label. In the heaters and some other equipment, such as the heaters, you will actually need to include energy streams. And this is where the second type of stream that we discussed in our previous content, the energy stream, this is where it comes in. You do actually have 2 ways of adding the energy stream, but let's try the first way, which is dropping an energy stream. As you can see, it has a different color. It's not a sky blue color, it's more of a purple, I guess. So energy stream, it recognizes an energy stream in the modeling environment. With that, we've added it, and we do label our outlets. Let's say heated propane. That's one way to add an energy stream. So for the second way, let's delete this energy stream that we dropped. For the second way, we just manually impute it. We label it the way we label our outlets. We label it and we can call it anything with that. I prefer calling mine E's. I use E's for energy. So let's say E-heater. Yeah, so with that, we've successfully added it. And it's not as straightforward as the mixer also. As you can see down here, we have a message in the yellow background saying unknown delta P, which means unknown change in pressure. So the heater expects us to give it a change in pressure. And since we are heating, we expect the pressure to go a little bit up, to go higher and increase in the pressure. But the thing about this is that if I'm trying to heat it to a certain temperature, I would actually need to find out the pressure, the exact pressure which it needs to exist at for me to hit that temperature. So it's more of a trial and error thing, because you can't say, but let me practicalize what I'm explaining. Let's leave our vapor fraction for the outlet still to be liquids, and our pressure, let's see, we're having it at a pressure of 30 bar. As you can see, we are hitting 77. If I wanted to hit something like 100 Celsius, it's more of a trial and error thing because I do not know the exact pressure that would get me there unless I do have it on ground. So the ASPEN HYSYS expects you to always give pressure, but for me, I just like I love doing a walk around. It's more like a cheat stuff, just giving you directly my temperature I need talking. Okay, so it tells me that let me just go over that one more time. Okay, I think we're on hold. Are we? No. No change in pressure. Let's go over it one more time. So you can see it tells us that a pressure in the stream heated propane is not found at requested conditions. It's telling us that it cannot exist in a real life scenario like this. So let's try a lower temperature. Let's say 70. Let's say I'm trying to hit a temperature of 80. With that, ASPEN HYSYS just automatically gives me the value of my pressure. In a heater, I'm more concerned with my temperature than my pressure. So if I have a specific outlet temperature that I'm targeting, I feel it's actually easier for me to just specify that temperature. But take note that this is not really advisable. This is not the best way to go around it. It's always better to give the pressure. It's more accurate. But if you do have an idea on what you're doing, I think this saves time to give the temperature directly. So we can just impute the pressure back, maybe 31 bar, and we're hitting 79. Let's say 32 bar. We're hitting the desired 80.8. So with this, we have successfully operated out heater. So remember, in a heater, we do need to add something extra, which is the energy stream. All right, so let's go over our fault equipment before we call it a day. As you can see, the fault equipment's having a blue arrow going up, the cooler. And let's drop another stream. And as usual, our convenient lazy or propane. Let's use the propane stream to define this new stream. Let's call it propane 2. So it has the same attributes as the first propane that went into the heater, but this time around is going into the cooler. Remember, inlet, we have the inlet stream on ground, which is propane 2. Energy stream, we need to label it if we're not dropping the new stream from the model palette. Hyphen cooler this time around. And for outlet, we do need to label that too. So let's call it cool propane. And as usual, we do need a change in pressure for this too. So in a heater, if we do raise our temperature, we do get a rise in pressure. So for the cooler is the opposite of a heater, so we expect the opposite process, which is a drop in the pressure due to the drop in temperature. We're still maintaining our same vapor fraction of liquids, which is 0. This time around, let's give it a pressure drop of, let's drop it to 10 bar. That means we're having a pressure drop of 7.2 bar, change in pressure. With that, you can see our temperature is dropping. So let's say I'm trying to take it to 5. I could just directly put the temperature up here, 5, and have my pressure to be 5.01, my outlet pressure. And with that, we have successfully operated the cooler. So before we round up for this content, I need us to go over 2 more important things. We're going to make it swift. We're going to be using the mixed carrier, something very important, and the heated carrier, something very important also. So for the part of the mixer, remember that when we were mixing with 3 inlet streams of propane, they were all in a phase of liquid, which was a vapor fraction of 0, pure liquid. And you expect that when we mix 3 streams of liquid, we expect liquids to come out as the outlet. So imagine if we're mixing an outlet of gas and an outlet of liquid. That's a stream having a vapor fraction of 1 and another stream having a vapor fraction of 2. So what do you expect our outlets to look like, the phase of our outlet? It's going to be a mix, obviously, a mix of gas and liquid. So let's practicalize that and see. We draw 2 streams, and we're going to call this, the first one, gas propane. And remember, the vapor fraction of a gas is 1. Let's give it a temperature of 30 bar, a mass flow rate of 100 kilogram per hour. Our composition, very, very important. Compositions. We'll put that back once more. Okay. Yes, and with that, we've successfully created the stream for the gas propane. Now, coming down to this, we're going to name this liquid propane, and we're going to copy the attributes of that same stream. All right, so remember, this is a liquid propane, and the vapor fraction for liquid is supposed to signify 0, but ASPEN HYSYS copied every single attribute from the gaseous propane, the gas propane stream down to the liquid. So we need to fix that up. So let's just erase the smaller flow with that. Okay, let's impute our mass flow to be 100 kilogram. Okay, so let's erase the 30 bar. So 30 Celsius, the temperature, so we can manually impute our vapor fraction, and ASPEN HYSYS gives us our temperature automatically. Vapor fraction of 0 since it's a liquid. Yes, and you can see that we've successfully created a liquid propane stream. And I want you, before we do the mixing, I need you to compare the attributes of these 2 streams. Every single thing should be the same, from the vapor fraction to the temperature to the pressure and the flow rate. These 4 attributes should be the same. Rather, the 3 attributes minus the phase fraction, because the difference in them is the phase fraction, where one signifies gas and the other signifies liquid. So the temperature, pressure, and flow rates are the same. The only difference is the phase fraction. One is liquid, one is gas. So we're going to be combining them to have a mixture as our outlet. Let's do that. Every single variable in this 4 properties. The three properties are the same. The only difference is the phase fraction. Remember, one is gaseous, one is liquid. So drop in our mixer. Double click. Let's pull this down to enlarge it. Remember, inlets. We connect our gas propane inlet, liquid propane inlet, and our outlet to be mixed propane. Right. So when you mix gas and liquid, you expect a mixture of gas and liquid. But remember, for our case, there's something peculiar. The temperature and the pressure and the flow rate are the same. The only difference is the phase fraction. The phase fraction, one is gaseous, one is liquid. So double clicking on it, you can see ASPEN HYSYS finds equilibrium between these 2 streams of gas and liquid due to their same temperature and pressure but different phase fractions. So it finds equilibrium. It's 0.5. It's at equilibrium. Equal proportion of gas, equal proportion of liquid. So if our temperatures or pressure varied, you would see that the vapor fraction would be tilting towards the gas or the liquid, depending on the variation. But for this, the temperature and pressure and flow rates are the same. The only difference is the phase fraction. That's why we're having the same properties. The only difference is the phase fraction, and it's in equilibrium. It's a phase in equilibrium, 0.5 liquid, 0.5 gas. So that's the first thing. One last thing I would like us to see is the operation of a heater, heating the boiling points of liquids. What exactly is a boiling point? A boiling point is the temperature at which a liquid starts to change its phase. Its liquid phase to gaseous phase. And yes, it's actually possible. ASPEN HYSYS, remember that we do have a function between temperature and pressure. In most cases, when you increase your temperature, the pressure increases, or when you increase your pressure, the temperature increases. So we're going to be doing that. We're going to try and change our phase due to change in temperature. And for this, we're going to be using water as our component, not propane anymore. If you do still have propane, all you have to do is just head back to the component list and change it. For that, you click on your properties, takes you up back here to your component list. We're not changing the fluid package, we're still working with Ben Robinson. So component list, as you can see, you still have your propane. All you have to do is click on propane, remove, and search for water, which is H2. Click on it and add back to simulation. So ASPEN HYSYS always asks you when you move from the simulation environment back to the component list, and you're trying to go back to the simulation, always asks you if you want to go back on hold mode, which is the pause mode. But for us to save time, let's just click no. We do want to go back on the play mode, the active mode. So with that, you've successfully changed your component, and this is going to be liquid water. We need our liquid water to change the phase from liquid to gas. And remember, liquid, the vapor fraction of liquid is 0. Let's give it a vapor fraction of 0. Remember the criteria for water to exist in gas, the conditions for water to exist in gases, in a gas form from our elementary science is that the water needs to be at a temperature of 100 and above, 100 Celsius and above, and at a pressure of 1 atmosphere, 1 atm. So for us to make water exist in a liquid form, we would need to make sure that the temperature of our water is less than 100 Celsius, and preferably at a temperature less than the 1 atm. But it's not much of a problem, so I feel like we could still leave the inlet temperature of the liquid water at 1 atm. For you to change the units, all you have to do is just click on this arrow and you can see atm. You click on that and let's give it a temperature of 70, a flow rate of 100, mass flow rate and a composition, as always, 100% water. You just need to add that back one more time. Okay, we do have one now. Mass fraction, 100% water. Not solved and not solved. That's stream. Okay, yeah, we're good to go. That was a consistency error. Remember the thing where you cannot assign 4 values to your stream creation, because ASPEN HYSYS always finds the 4th value for you automatically. So that's why we're having an error. We imputed 4 values for our stream. We're supposed to impute only 3, and as you can see, we have 3 values manually imputed for the temperature, which is 70 Celsius, the pressure, which is 1 atm, and the mass flow rate of 100. So our water exists at a phase fraction of 0, which is purely liquid. And we're going to be using a heater to hit the boiling point in order for our phase fraction to change from liquid to gas. So remember the inlet for the heater, which is our liquid water. Outlet. So water in a gaseous form is called steam. So we name this outlet as steam, and we give it an energy stream label. Let's just call it E1. And with that, we head to the worksheet. This is where we select the conditions of our outlet stream. Remember, what we're majorly after is the vapor fraction, the phase fraction. And for water to be in gas, it means that the phase fraction is 1. So select 1. And the temperature, let's allow ASPEN HYSYS to give us the temperature. Let's impute the pressure. So let's impute the pressure of 1 atm. We're still on 1 atm. And with that, ASPEN HYSYS has given us a temperature of 99.96 Celsius, approximately 100. Remember, from our elementary science, we do know that water boils at a temperature of 100 Celsius at 1 atmospheric pressure. With that, we've successfully changed our vapor fraction from 0 to 1. So these are all factors that we need to bear in mind when we're carrying out modelings and simulations for different processes. We'll be seeing change in temperature, pressures, and vapor fractions. To some extent, we'd still be seeing change in our flow rates due to some other phenomena and use of other equipment. But for today, this is what we do have. If you followed us down this far, please make sure to subscribe, like, and click on the notification icon so that you can motivate us to create more content like this. Thank you very much.